Okay, so what we've got here is a short lesson, and I'm sorry this is coming to you a little late in the day. Make sure your brightness is turned up because I'm actually trying to cast light on this with a lamp now. So what we're going to try to do today is talk about the new definition, just the dimension. Originally, this lesson was combined with 4.6 because it's so short, but now we are going to kind of learn it by itself just to focus on it. So we are going to do a couple little proofs, kind of using something we learned in 4.4, and then we're going to do a little bit of practice finding what the dimension of a vector space is. So our first theorem is that if a vector space has a basis, vectors b1 through bn, then any set that in V, so any set of vectors that are also in the vector space that contains more than that number of vectors, n vectors, must be linearly dependent. So we're going to prove this using a change of basis, meaning we're going to go back to 4.4 and we are going to create a set. So we're going to say, let a set of vectors, let's say V1 through VP, and I'm intentionally using a different subscript there, be in V. So basically all we're doing is we're creating a set of vectors that are in the vector space. We already established that the basis for V is B, which is the set of vectors B1 through Bn. Okay, then we are going to assume, we're going to let n, the number of vectors in the basis, be less than the number of vectors in the set we created. Okay, because that's what we're testing. Any set in V containing more than n vectors must be linearly dependent. Okay, so the number of vectors in our set is greater than the number of vectors in the basis. Okay, so let's make a new set. Making a new set using a change of coordinates matrix P sub B. Okay, so we're going to change each of these vectors to be in the basis B. Okay, so there will be, okay, notice that P sub B will have n columns. And if you're confused why it will have n columns, in 4.4 we talked about making this change of coordinates matrix PB. It's just made up of, is a matrix that uses the basis vectors as its columns. So if there are n basis vectors, we have n columns. Okay? All right. So if we make a new set of vectors, then our new set, which will be, and I'm going to use the notation we used in 4.4, which was V1 with respect to basis B, all the way up to VP with respect to basis B. Okay. This has new set, okay, has P vectors, because we had, and that makes sense, because we had to transform all of these vectors to be in the new basis. So this has P vectors, but, the important part is, but each vector, VP, with respect to basis B, has n entries. Okay? And you can think about that because we had to, n was the number of columns in PB, which meant that, okay, each vector, let's say V sub P, was created by using a linear combination B1 through Bn. Oh, I forgot my Cn. Okay, and V sub P with respect to basis B is the coordinate C1 through Cn. Because remember I was about to say last class, in 4.4, we talked about how the coordinates that we are creating out of this new is kind of looking at the coefficients of the linear combination we made. So this has to have n components because we had to use n constants multiplied by each of the n basis vectors. So going back to this many vectors, we have p vectors here, but each of them has n entries. Okay, so that means if we put them, thinking about this in a matrix, okay, that means that we have p vectors and n entries. As shout out to Richard here likes to say, this would be longer than it is tall, which means since we know that n is less than p, the set of vectors with respect to the basis b is linearly dependent, and okay, since set 2 that we made is linearly dependent, then the set v1 through vp is linearly dependent. Okay, QED. So let me go over that one more time. What we did was we created a set of vectors in the vector space, knowing that there was already a basis for that vector space. We let there be more vectors in here than there are in the basis. We then used our 4.4 knowledge to change these vectors into vectors with respect to this basis. We used a change of coordinates matrix. What was important about that was the number of vectors did not change, but because we changed it into being with respect to the basis b, we guaranteed that each of these vectors has n entries. And they will have n entries because those n entries represent the coefficients we multiplied by the basis vectors to make a linear combination for that vector. So our n entries are c1 through cn. That meant, since we knew that p was greater than n, that we had more columns than rows. And since we had more columns than rows, that set was automatically guaranteed to be linearly dependent. And since that set, which is isomorphic to this set also had to be linearly dependent. Cool, so that's our one proof, okay? So kind of just assuming some things and following it through. Theorem 10 though, our next one, if a vector space has a basis of n vectors, then every basis has to contain n vectors. Okay, because remember in I think 4.3, we talked about how to create a basis. And we're saying there are multiple ways to create a basis, but each basis has to have the same number of vectors as all of the other bases. That's what we're talking about here. So we're going to do a proof by contradiction, which basically means we're going to assume that what I just said is false, contradiction, and see if we can get to a statement that is definitely untrue. So I kind of filled this one out already for you, but so we're supposing that b1 is the first basis, and it has exactly n vectors, and then b2 is any other basis. Remember that we can have many, but b2 is any other basis, and by definition, what's important is that b1 and b2 are both linearly independent, otherwise they wouldn't be bases. Okay, so by the theorem we just talked about, if b1 has more vectors than b2, then b1 has to be linearly dependent. We just proved that if a set has any more vectors than the basis, then that set is linearly dependent. But that can't be true because b1 is supposed to be a basis, which is linearly independent. And then for the same reason, if b2 has more vectors than b1, then b2 must be the one that's linearly dependent, because any set that has more vectors in it than the basis does is automatically linearly dependent. But we assumed at the beginning that b1 and b2 were both bases, so it should be linearly independent. Okay, so each basis, basically, if we assume that one has more vectors than the other, then it can't be a basis because it would turn it into being linearly dependent. Okay, so they have to have, okay, so therefore, all bases who knows? All bases have equal numbers of vectors. Okay. All right, so those are our two proofs for today. Okay, so let's talk about a couple other things. We'll work on more about figuring out what a dimension means. So, dimension. Okay, if V is spanned by a finite set. Okay, so that means if we can get to all vectors in the vector space using only a few vectors, and by a few I mean like it could be 3, it could be 10, it could be 20, who knows, but it has to be finite. Okay, then V is said to be finite dimensional, and the dimension of V, written as dim V, okay, we got more abbreviations here, is the number of vectors in the basis. Okay, which makes sense because that would be the number of vectors that span, I would have to use to span all of V. Okay, quick definition. The dimension of the zero vector space is defined to be 0. Okay, so the zero vector space technically is a vector space all by itself, but we define the dimension to be 0. Okay, and that also makes sense. You're like, wait, there's one vector in here. Why is the dimension not 1? Well, in order to have a basis for a vector space, you need to have a set of linearly independent vectors. And way back when, we defined the zero vector all by itself to be linearly dependent, because anything can be used to make the zero vector. So we just went ahead and just cleared the error and said the dimension of the zero vector space is 0. There are no vectors in the basis. Okay, it's just the vector itself. All right, if V is, and this is a fun fact, if V is not spanned by a finite set, then V is said to be infinite dimensional. I want you to look that up. Just go Google some examples of something that's infinite dimensional. It's a good activity for quarantine time. Okay, think about infinitely dimensioned sets. All right, so a couple of examples. The standard basis for P3, and in case you have not picked up on this yet, P3 is all polynomials of at most degree 3. Okay, so the standard basis would be what elements do I need to create all polynomials of at most degree 3? I need a constant, I need t, t squared, and t cubed. So those are my basic elements to create a third degree polynomial. So the dimension of this is 4. There are 4 vectors, quote unquote, in the basis. Okay, so and then in general, something for your note card, the dimension of a polynomial set, all polynomials of a degree at most n, is n plus 1. And you can think about that because we need a term or a vector that represents each degree, including 0. So usually when we say a third degree Taylor polynomial, we don't think about the 0 degree term, but we need it to make all polynomials of at most degree n. Okay. Now for vectors that we've been looking at for quite a long time, the standard basis for Rn is E1 through En, okay, where E1 is something like 1, 0, all the way down, and the last one would be 0 all the way down, and the last entry would be 1. Okay, so that's what we call E1, that would be called En. You can also think about them as being the columns of the identity matrix, but since this and this match, we know that the dimension of R3 is 3. Okay, easy. So let's look at example 2. Okay, we want to find a basis and the dimension of this subspace. So this subspace is all vectors that fit this condition. To me, this looks like they were created from a very specific matrix. Okay, so it would be basically the W, I would say, is also the column space of A when A is a matrix. Now let's see, how many variables do I have? I have 4 variables, which means I needed to be able to multiply by a 4-dimensional vector. So I'm supposed to have 4 columns, okay, because this would be A, B, C, and D. Okay, so A is just this part. This is just for our own reference. So the first row would be 1, 1, 2, 0. Second would be 2, 2, 4, 1, 0, 1, 1, 1, and 3, 0, 3, 1. Okay, so really, W is the column space, all linear combinations of these vectors. So we want to know, okay, are these columns linearly independent? Okay, because we're looking for a basis for this subspace. We're basically looking for a basis for this column space. So when I row reduce A, and to save us some time, I did it in my calculator, I get the matrix 1, 0, 0, 0. So I know that column 1 is linearly independent. Column 2 is linearly independent. Column 3 is not. Column 4 is linearly independent. So a basis for W is the original column 1, the original column 2, and the original column 4. So 1, 2, 0, 3, 1, 2, 1, 0, and 0, 1, 1, 1. Remember, it's important that you write the original vectors because these could provide different linear combinations than these vectors could. Notice that I can get vectors that have a third component other than 0. I could not get that from the final 3 vectors here. So make sure when you're making a basis, you go back to the original vectors here. Well, a basis for the column space, you go back to the original vectors here. The null space, totally different. Okay, so there's the basis, and then we want to know what is the dimension. So the dimension of W is 3, because there are 3 vectors in the basis. Okay, not so bad, right? All right, this feels like, again, I hope you're starting, if you're following along with the lessons, I think you're starting to see kind of a rhythm of where this is going with the column space and the null space and why we did that first. So again, a zero-dimensional subspace contains only the zero vector. Excuse me, only the zero vector. So that would be a point in space. A one-dimensional subspace would be the span of one vector. That's not the zero vector. I don't know why I said it was in R3, but regardless, if we're thinking about this geometrically, I think that's what I said, R3. The subspaces are a line through the origin. Okay, and remember, it has to go through the origin if it's going to be a subspace, because the zero vector has to be in that subspace. Okay, two-dimensional subspace then, if I have 2 vectors and they are, again, not linearly dependent, then the subspace is a plane through the origin. Again, has to go through the origin in order for it to be a subspace. Otherwise, we don't contain the zero vector. All right, and last but not least, the three-dimensional subspaces. Okay, 3 vectors that are linearly independent. A three-dimensional subspace is R3. Okay, that is its own subspace, or vector space, if you want to think about it. Okay, all right, so if you printed out the notes, which I doubt maybe you did, but Theorem 11, let's look at a couple other things, and we are almost done, in fact. Okay. So H is a subspace of a finite dimensional vector space. Okay, so we've got H a subspace, V a vector space. Any linearly independent set in H can be expanded to be a basis for V. So the reason I'm saying that it's not already a basis for V is I'm not 100% sure that a linearly independent set in H would span all of V. Remember that H, a subspace, can have specific conditions that don't have to be true for the entire vector space. But since the set of vectors in H are, 1, linearly independent, because we're assuming that they're a basis, or they're linearly independent. 2, since they're already linearly independent, they're already like most of the way through a basis. But 2, because they're in H, that means they're also in V. Okay, because remember we've got our kind of concentric circles happening here. If this is V, this is H, maybe it's got its own conditions happening in here, its own kind of self-sustaining conditions. So if I have a basis for H, I don't automatically have a basis for V, but I can expand, I can use that what I have and expand it to be a basis for V. Okay. Also, if H is finite dimensional, then either the dimension of H is less than or equal to the dimension of V. Again, equal to because it could be that we could use a basis for the subspace as a basis for the whole vector space, but maybe I'm not sure. So as an example, I'm going to let H be the span of these 2 vectors. They are linearly independent. Okay, so this would be a basis right here for a span of, this would be a basis for H. H is a subspace of R3. Okay, and you can test that out yourself. You could go back, you need to prove This would be a good one to show the 3 conditions that you need to prove that something is a subspace. But I do know the dimension of H is less than the dimension of R3 because there are only 2 vectors in the basis here, where I need 3 vectors to be the basis for R3. But I can expand this set to include another vector, 0, 0, 1, so that it could span this basis here. Is still linearly independent, and now it does in fact span all of R3, which is good. Okay. All right, and last thing before we get to some last couple examples, I realize it's a little bit longer than I thought that I liked, but okay. If V is a p-dimensional vector space, okay, and p is greater than or equal to 1, then any linearly independent set of exactly, keyword, exactly p vectors in V is automatically a basis for V. So when I say p-dimensional here, I mean p entries in each vector. So if there are p entries in each vector and p vectors, that means that if I were to put it in a matrix, rows equals columns, which means that I would make a square matrix. And because I said that any linearly independent set of exactly p vectors, that makes me know, since I have a square matrix, I also know that there's a pivot every column, which means, since it's a square matrix, there's also a pivot in every row. So therefore, my linearly independent vector set of exactly p vectors, not only is it linearly independent, it also will span all of the V that I am looking for. Okay, so that makes it automatically a basis, and that's super nice. All right, so let's take a look at some last 2 examples here. Okay, so first, I want to show that this is a basis for P2. I feel like we already did this example. I feel like we did this example in literally like the last lesson. But because of that, I'm going to skip it. But I will help you out if you want to pause real quick. Use the change of basis, or change of coordinates. Change these into vectors. Okay, so example, all right, I'll just start it. Since I have polynomials of at most degree 2, I'm going to need 3 entries. 1 for the constant, 1 for t, and 1 for t. Oh, you can't see that. 1 for the constant, 1 for t, and 1 for t squared. So my first vector for the polynomial just t would be 0, 1, 0. My second vector for the polynomial 1 minus t would be 1, negative 1, 0. And the last one would be 1, 1, negative 1. I don't know why that took me so long. Okay, so we want to show that these 3 vectors are a basis for R3. And then by showing that they're a basis for R3, which is isomorphic to P2, we can show that these vectors are a basis for P2. Basically, we just need to show that these are linearly independent, because my theorem that just said this, any 3 vectors in R3 that are linearly independent automatically form a basis for R3. And again, because R3 is isomorphic to P2, whatever forms a basis in R3 will form a basis for P2. All right, but let's look at the last problem and actually try to do that one. Okay, so dimensions, wrapping it all back up into column space and null space. Okay, we want to find the dimension of the column space and the dimension of the null space. That's going to mean I'm going to need to find the kind of row reduce a little bit to make sure that I've got some linearly independent vectors. I know that these are going to be linearly dependent, again, because there are more columns than rows. So if I row reduce, I can already see that column 2 is linearly dependent. And so, in fact, is column 4. So maybe I don't even need to row reduce that much, but I will anyway. Okay, so here's my row reduce matrix. Okay. All right. So column A, and maybe I'll just go ahead and practice writing out my column space. So the column space of A is the span of the linearly independent vectors from the original. So the linearly independent vectors were vector 1 and vector 3. So original vector 1 and original vector 3. So this is what the column space looks like. This is a description of the whole column space. So that means, since these are linearly independent, the dimension of my column space, because this forms a basis for my column space, is 2. Okay, now for my null space, I actually have to write out the solutions. So my parametric vector form of my solutions will have 2 free variables. Oh god, let's see if I can do this out of the top of my head. We'll have x2, and again, they will have 4 entries because I have 4 variables. So these need to be subtracted to the other side. So -2, 1, 0, 0. And x4 is my other free variable. I'll have -4. Oh, I'm sorry. This is not the full row reduced matrix. It doesn't really matter. That's why I had to pause. Sorry, guys. Alright, it's 0. Okay, now I'm ready. I got freaked out because I was like, wait, is x1 dependent on x3? No. Okay. Alright, so -4. Oh, x3 doesn't depend on anyone. Hype. x3 is just equal to 0. Okay. 0, 0, 1. There we go. Okay, and if you need to write that out, if you need to check my work, just pause real quick and write these out as vector equations before you go directly to the parametric vector equation. So, my null space is the span, meaning all linear combinations of these 2 vectors. Notice that the null space has nothing to do with the original vectors that are in the matrix. Alright, so my null space is the span of those 2 vectors, which means these 2 linearly independent vectors are the basis for my null space. So, the dimension of null space of A is 2. Okay? Now, my hint from above. Maybe you'll see this as we go into next lesson. The dimension of column space of A is the number of pivots, and the dimension of the null space is the number of free variables. If you add those together, because this is the number of basic variables, this is the number of free variables, you should get the number of columns for A. Okay? That's a great way to check to see if yourself is correct. Yourself is correct? Alright, whatever. It's getting late. Okay, one more note, because I want to make sure we clarified this. A note. I already wrote this, so I'm just going to explain it. So, to span an entire dimension, like R2 or R3, and I'm looking at span, okay, that means I need to be able to create any vector in R2 and any vector in R3. I have to have a pivot in every row. That's what chapter 1 was about. Okay, so that means for R2 I would need to have 2 rows of pivots. For R3 I would need to have 3 rows of pivots. Okay? And to write a basis for either one of these spaces, or in general even, the vectors have to be linearly independent, which would mean a pivot in every column. Therefore, a basis for an entire dimension like R2 or R3 has to have 3 vectors for R3, or let's just say n vectors and n entries. The same number of vectors as it does entries. Okay? We're going to assume that I'm not using vectors that are in R3 like 1, 0, 0 and 0, 1, 0 to span R2. Okay, we're just going to stick with vectors in R3 that are spanning R3. Vectors in R2 that are spanning R2. Okay, so in order to span R3, or to write a basis for R3, I need to have exactly 3 vectors. But that's different for a subspace, because a subspace, I'm not trying to get to all of the vectors in a certain dimension. I'm not trying to get to all of R3. There are just specific conditions. So for my subspace that I created here, A, B, 0, this is in R3 because it's a 3-dimensional vector, but H is the span of 1, 0, 0 and 0, 1, 0, okay? Because I only needed the first 2 entries. So the basis for H is only 2 vectors, even though each vector in the basis has 3 entries, 3 dimensions. So the basis for a subspace does not need to have equal entries and vectors. Okay, I wish I could say here, does that make sense? But hopefully you'll just tell me. Okay, we have office hours. Okay, so a basis for a subspace just needs to be a set of linearly independent vectors that span this subspace, that are capable of creating all of vectors that look like the conditions that were set out. That's it. Okay. Okay, and if you need another example, look at what we just did, example number 2. All right, thanks for bearing with me. I know this was a longer video than I thought for only a couple pages of notes, but hopefully you have a great weekend, and we will see you next week to pick up with 4.6.